It's a little bit,
Okay, it's a minute
a
after.
little bit later than that.
Well, you know, 2012 was like a relatively good year for me. That was before some bad stuff happened.
It's a very vague statement.
You're the only one. Yeah, I was definitely thinking about sleeping in, but like that's not an excuse because I went to bed early.
My coach is ready for something.
Golly, I don't know, maybe I was,
You're a popular guy, Doc.
yeah, like I said, 8 a.m. class are always popular. So it's gonna be fun next semester when you
Yeah,
guys
I was so
okay.
excited for the 9:30.
Don't blame me, it wasn't me.
I still have the 8:50. Oh.
It was, every semester it's always been a 9:30, except and then like some
us.
classes changed. I'm like, oh, well, we should move organic chemistry at 8 o'clock. I'm like, I don't care. I'm like, I've always been a morning person, but I'm like, boy, oh boy, you know.
Wait till we tell the rising sophomore.
That 8 a.m., those 8 a.m. classes are a little bit tough for you guys there sometimes, so.
Yeah, I went home and just started ranting about it to my mother. I'm like, Mom, organic chemistry is supposed to be at 9:30. I was gonna have a whole extra hour of sleep in the morning and
You
just
guys would just stay up late anyway. Doesn't matter. You guys get the same amount of sleep. I'm not falling for those tricks anymore. Anyway,
Are you excusing me of having a poor sleep schedule?
I'm not excusing you, I'm accusing you.
Yeah, that's what I meant to say. That is what I.
See, the real trick is not, it doesn't matter when you go to bed, is that you have to you wake up at the same time every day. That's what actually makes a difference, so.
Yeah,
But
I have moments.
anyway, so we do have a couple of things to go through today. We gotta finish talking a little bit about batteries and start to get into a little bit of the calculations that go along with how we can calculate the potential for when we have these voltaic cells, right? So when we have a solution of metal with some kind of solid metal in there, and you know the cathodes and the anodes, and we talk about the salt bridges and all these kind of things, and the functioning aspect of how these voltaic cells work, right? So today what we're going to do is take the voltage values for those and figure out, you know, what the potential for one of these cells is going to be, right? And we're going to relate that back, or we're going to draw in a little bit of the ideas of equilibrium and Gibbs free energy. And so we're going to talk about a relationship between the cell potential and Gibbs free energy and equilibrium here also, right? And so we'll talk about things not at the standard state and yada, yada, yada. Basically just saying, hey, look, here's some equations how you can calculate E naught or E of the cell at different conditions is all it comes down to, okay? So we'll have a couple of equations that come out with that. And that should take us basically through the rest of the chapter here. The rest of it is just kind of dealing with different applications of certain equations that we'll introduce. And then that'll be the end of the electrochemistry, and then we just have one more chapter-ish to go after that, right? Although the last chapter there's going to kind of be not really a full chapter, right? We'll see how far we get, who knows, right?
You want to hear something really sad though?
Sure.
One of the people in Dr. Tom's class, their last name is Gibbs, and he already calls them that, and
Yeah.
refuses to use their first name, just calls them Gibbs all the time.
Mm-hmm.
They're about to hit Gibbs free energy. He's gonna make so many puns, like every single class on this poor person's name.
We can only hope, right?
Are you the only one teaching yoga?
Yeah. Yeah, they're stuck. No other choices. Thought you'd get away from me, huh?
No, I never had you as your professor over Tom.
Oh man. Well, Dr. Tom doesn't teach OCHEM at all, so it's either me or Dr. Barbosa that teaches OCHEM. But
We'd rather have you.
well, I mean, it's whatever, right? To be frank, you know, and not to get on too far of a tangent here, it's It's always good to get different professors for your classes, because otherwise you get the gospel according to Patrick, right? And you learn chemistry my way, and you see my interpretation of chemistry, and you hear my lame jokes over it, right? You guys hear me. And don't get me wrong, I'm awesome, but the point being, right, you guys need to hear this from different sources also. Like Dr. Barbosa has a very different approach to organic chemistry than I do, right? Yeah, I mean, in some of the, not overall, right? Obviously, we teach the same things, right? But, you know, at the end of the day, the way he explains things, the things that I focus on are a little bit different. You know, and part of the reason is he's a pharmaceutical chemist, right? He's a medicinal chemist, right? And I'm an inorganic materials guy, so I just look at things, we look at things from a different perspective is what it comes from. Anyway, good job getting me off topic. Not hard to do, you know, as professors like to talk about ourselves. Anyway, so we ended here with probably the first equation that we need to pay attention to, and that the potential of the cell, right, E naught of the cell, is E naught of the cathode minus the anode. So what we have to remember here is we have to remember about what reaction happens at the cathode and what reaction happens at the anode, right? So we talked about the big red cats, right? So we know the reduction is what happens at the cathode, and so oxidation here happens at the anode is what it is.
Could you explain the big red cat thing one more time?
Yeah, it's just a stupid saying that I have for remembering what is going on in a voltaic cell, right? So let me scroll up here. There you go. There's a mosquito flying around.
Those are fun.
Right? Yeah, this is fine. This is right. So all I was saying with the big red cats is the cat's part just stands for the cathode, right? The red stands for reduction, right? The big just means that physically, right, this metal piece here is getting bigger. We're depositing metal here, right? So the solution becomes solid metal here, right? And the light just means that the cathode is the positive end of it. That's all it means. So the light, the big, the red, and the cats just refer to specific things that are happening, right? The cathode's positive, that's the light, right? The reduction happens at the cathode, and the cathode physically gets bigger.
Wait. The cathode positive is the light?
Mm-hmm.
Huh?
If you like something, it's a positive thing. I don't have a better way of putting it.
Okay.
I positive big red cats doesn't make sense. Right, so it's just a phrase. You guys don't have to use it. I'm just telling you what I do. Right? Just memorize
Just
it.
confused as to what part of what goes to each bit of the acronym.
Like is positive, red is reduction, cat is cathode, big just means it's getting bigger. That's all it is.
And you?
Mm-hmm.
You, like the I part?
That's to make it a statement. Right? That doesn't actually mean anything.
Hey Yana, come back. Your dreams were your ticket out.
Okay, so we got a 25% increase in attendance today. Anyway, so at the end here, the important part when you guys are trying to calculate the E naught of the cell, we do have to pay attention to what's reduced and oxidized, right? That's going to tell us what happens at the cathode and what happens at the anode. Okay? Remember, what we're dealing with and the equations that we're dealing with are the half cell reductions. Okay? So whether we're doing a reduction or oxidation is going to change the value of the potential that we draw out of the tables of half reactions. Okay? So, I forgot to start with some prayer here. So anyway, we'll pick up this problem here in just a second. Let's get started with prayer. Lord, we just thank you yet again, Lord, that whenever we think about it, whenever we can, and that we do it more often, Lord, we can just turn to you in prayer. And that you listen to us, Lord, and you love to listen to us, and you want us to spend that time with you and just grow our relationship with you, Lord. And so we just pray just to put that thing on our heart, Lord, just to make us desire to spend time with you more, Lord, and just help that time to be fruitful and beneficial for us, Lord. But we just pray that that time spent with you can also be reflected to others around us. Lord, help us just to spread your word and your kingdom and what it is that you would have us do here at this time, at this place. Lord, just give us the strength that we need, Lord, just give us the focus that we need just to walk through this day, but also to walk behind you, Lord, in the footsteps that you lay for us. We just pray this in your name. Amen. All right. So, if we have an example here of zinc and copper, right? If we have an example of zinc and copper, so what's going to be going on here then, right? So if we have these two specific reactions, and I'll go ahead and define them as one is getting oxidized and one is getting reduced, okay? The E naught there tabulated, that's pulled directly out of the appendices, right, or those tables that you guys have, right? But remember, okay, if you're taking a look at the zinc reaction there, the way it's written now is as an oxidation, right? It's a loss of electrons. And what we pull from the table is a reduction. So I flip, right, I flip the equation around. And if I flip the equation around, the negative 0.76 becomes positive 0.76. You guys with me on this one? Everyone following along with that, right? So all I'm saying is, I'm telling you one is getting oxidized and one is getting reduced, okay? Right, so if we just scroll up here for a second, let me erase. Right, here's our zinc, right? The way it's written out of the table is as a reduction, right? Reduction, half reaction there. If I'm telling you this gets oxidized, I flip this whole equation, right? And if I flip the equation, I flip the value for the potential there, right? I multiply everything by -1 is what we're doing. Good? All right. So then bringing in the equation that we just had there, E naught of the cell is equal to E naught of the cathode minus E naught of the anode, right? Reduction happens at the cathode, right? And that means oxidation happens at the anode. Let me maybe put some different colors here then, right? Just so you guys are following along. Okay? So E naught of the cell, then in this case, if I can spell cell, is equal to, right, our 0.34 minus our plus, excuse me. So minus our 0.76, right? That's coming off of there, which is going to be equal to that right there, right? So the minuses is where we're getting this value for there, right? You guys with me on that one? So why am I showing you guys this? So I want you guys to think about two things, right? Remember, when you flip the equation, right, you have to flip the E naught value there, right? But what's going into our equation here is the value that comes out of the tabulated, out of the half reaction table there, okay? Remember that minus sign is the important thing. This is the most missed part of these types of questions. Okay, you guys forget to put a minus sign in there and then your values get thrown off, okay? What's up?
Why is the tabulated and final for copper, why are they both positive?
Because it is, we pull that reaction as it is written out of the table. Right, that is a reduction of copper right there, right? And we have half reactions for the reduction of whatever metal species, right? And it just happens to be 0.34 volts, right? That's all it is.
Okay.
You guys with me on this? Right, the math isn't tricky. The only tricky part is just remembering the positives and the negatives, right? And so E naught in this case, right? What is it? 1.1. Yeah, it's 1.1 volts. Got it? Good? So, what do you have to know when you're going to start to put together more complex problems like this? One, how to read the tables, right? You know, the reduction half tables, that's not too hard. And then you're going to have to remember what happens at the anode and what happens at the cathode in terms of reduction and oxidation. Okay? That's it. So, as long as you guys know that stuff, then you guys should be able to work through these problems here. So, as another example, right? Now it gets a little bit more towards what we might end up seeing as a problem in the book. Right? So what is E naught for a nickel, right, silver cell? Okay. So you guys would look, right? You guys would look on the table there to find where silver and nickel are. Pay close attention. Some metals have different oxidation states. I think we have a problem coming up here. Okay, some metals have different oxidation states. So when I tell you it's nickel 2 plus, make sure you guys are finding the nickel 2 plus half reaction. Okay, not nickel 4 plus in case it would be on there also. Okay.
Does nickel come in 4 plus?
very rarely, right, but I don't even think it's on any of the tables, but I'm just, as an example, right? So anyway, right, so remember, we learned this last time, the convention there is that the anode is on the left and the cathode is on the right. So when you guys see that notation up there with the splashes and all those kind of things, it's telling us where the anode and the cathode is, so it makes life a little bit easier, right? So cathode minus anode, right? So we just pull our value for the silver into there, right, the plus 0.799, and then our anode right here, we just pull the negative 0.25. And we get our value for that out of there also. So, good? Everything all right here? Kind of, sort of? Okay, so see what you guys can come up with now, looking at this here. Real quick, what in the world is an SHE? That's your standard hydrogen electrode. Right? Remember what these other things that we talked about last time is that we talked about we need a reference in there. We can't measure absolute, we can only measure relative potential, okay? And so we set the standard hydrogen electrode, right? And that's our 0, essentially, is what it is. So when you guys are looking at your appendices there, I don't know if I borrow this for just a second. Why do you have a pothole in this?
It's a microfiber face cloth.
Oh.
Makes it smart.
Yeah, okay. So if you take a look at Appendix E, it should be in here. Let me take a quick peek. Otherwise, this is about to flop really hard. That'll be good. Yeah. There it is. Okay, so the bottom of the left-hand column has your standard hydrogen electrode there. That's equal to 0, right? The one that you were looking at right there, right? The one that's equal to 0, right? So everything is relative to that from there. Right? You got it?
Mm-hmm.
So if you guys see something referenced as that standard hydrogen electrode, right, its potential is 0, there you guys go, okay? So see what you guys come up with here. See what information you can pull out of this problem. See if you guys can answer the question here. What is E naught for the nickel half cell? Even though the answer was on the previous slide. So, tell me some important bits that we can tell out of the way the question's asked there.
It's reduced.
We're kind of jumping ahead here a little bit, right? So we got nickel, nickel 2 plus, we tell it's aqueous, it tells us it's 1 molar. That's gonna be important, not right now, right? But it's important to always pay attention to what the concentration is for the solutions there, right? So remember, that's one of our definitions that we had there, right? We assume that our concentrations are gonna be 1 molar, else we have to go back and we'll see, we have to do a couple of different, or we'll have to use a different equation basically is what it is, okay? It's connected to standard hydrogen electrode, okay? The nickel electrode loses mass over time. So what in the world is that telling you right there?
An anode?
Mm-hmm.
It's an anode?
How do you know?
Because the cathode gains less?
There you go, right? So this is just one of those things of knowing what happens at either end of the voltaic cell, right? If you're at the cathode, you're going to be gaining mass, and so at the anode you have to lose mass, right? So if you're at the anode, because you're losing mass, what reaction is happening there?
Reduction.
Oxidation.
Oxidation, right? The big red cats are going to get you at the end there, RC. Right? Right?
Wait,
but-
so nickel is being oxidized?
Mhm.
Okay.
So if nickel is getting oxidized, if it's losing mass, what in the world is the reaction that's happening? Well, what it's saying is this: nickel solid, right, is turning into nickel 2 plus aqueous plus 2 electrons, right? Because what do we mean by losing mass? We are consuming some of the solid nickel. That's what it's telling us, okay? You guys with me on this one? Okay. So how is that equation written? Well, that is the definition of an oxidation, right? A loss of electrons. So good, we know it's at the anode, we know it's an oxidation, we have the equation, right? It tells us information about E naught of the cell, right? So just to re-emphasize. Okay, so we know E naught of the cell is equal to 0.25, okay? That means E naught of our cathode, right? This is our standard hydrogen electrode then, right? And E naught of our anode, this is going to be our nickel, right? Nickel 2 plus. Okay? Everybody with me on what I'm doing so far? Right? So it asks us to figure out what E naught of the nickel half cell. So basically we have to solve for E naught of the anode, right? That's all it's saying.
Don't we already know that E naught of the cathode is 0?
Well, that's the whole point, right? So we know this is equal to 0, and so then E naught of the anode is just going to be equal to negative 0.25, right? But the point being this, that would this change any, right? If we didn't have the standard hydrogen electrode there.
No.
No, right? All that would change is that, you know, E naught of the cathode wouldn't be equal to 0, and we'd have to, you know, rearrange a little bit there, right? Because all we do is we have an equation with 3 variables, right? E naught of the cell, cathode, and anode. So I have to give you information about 2 of those to figure out what the other one is, right? Good? Not too bad, right? So paying attention, reading what the problem is telling you about what's gaining or losing and all these kind of things. Extremely important. Okay, see what you guys can come up with here. Probably will need your book, or look up some of the half cells there. Because I don't think this, or was I smart enough to put this in your notes? Nope. Oh, they got 2 tables in your book there too. Oh, that might be useful. There's that one. Does it have the zinc on there also? I'm sure it does. It's such a common one. Yeah, there it is. Right.
That's at 25. That's hard.
Yeah. We assume it's room temperature. That's fine. Yeah. Yep. And it's going to be in Spanish.
That's okay.
What the hell is ill battery? I don't know.
Can you make it French instead?
I don't mind it. It's not French.
I can say one thing in Spanish.
I bet
Donde
you can-
está el baño?
You know what queso is, you know what burrito is.
I took Spanish for too long.
There you go. You know what Espanol is, you guys know a lot of words mixed up. Okay, so how do we start to approach something like this? What do we need to do first and foremost?
Turn zinc into an oxidation.
Well before that.
Right.
Write the equation.
Before that even. You're looking at it. What do we need to do first?
Write the top reaction.
Find the stuff in our appendices, right? Find the information of the half cell reactions, right? That's what we need to find. So we take a look somewhere to find information, and we will find that, right, Fe3 plus an electron goes to make Fe2 plus, right? And that tells us that plus 0.771, right? And then we find somewhere else with zinc 2 plus 2 electrons, right? Goes to make zinc. I should be careful and of the states here. And this is negative 0.763, right? Those are the values that you guys got? Cool. Right, there you go. You guys got the answer now?
No?
No. What does this tell us? So now we have to think about something that we, I think I had a slide for you guys about information that's useful, right? So let me scroll back up here for just a second to draw that point back. Cool. So points 3, 4, and 5 are probably the most important things on here, right? So the more positive something is, the easier it is to reduce, right? The less positive something is, the easier it is for it to oxidize. Got it? I think you guys understand that, right? A species on the left will oxidize any right below it. Okay, that's going to be the important part here. Now, this is where we have to be careful, right? Because Appendix E is not, right? What we mean here is if this is ordered by voltage, which, Kayla, you said, what was it, table 20.1? The one that you were just looking at there?
20.1
Was it? Okay, so table 20.1 is a more condensed list that's tabulated by voltage there. Yeah. 871 or?
I have a different book.
Oh, you guys have
I have
different
the
books.
I have the older version.
Oh. I didn't
It's
even realize that.
863 and then the current one.
So for some people,
That
it's
helps.
863. What did you say?
863.
yeah, there you go. 907.
Okay, cool. So that table there is tabulated by voltages, right? So then we can take a look at this right here, right? I didn't realize you guys have different versions of this.
I just have the older one.
No, that's okay. Yeah, no, apparently a couple other of you guys do also. So, okay. So what does that mean? So we scroll, right? So when you guys are looking at your table, and hopefully that, I think both of those are on table 20.1 there. Yep. So you guys see the iron 3 plus is on the left, right? And the zinc is over here on the right below it on the table. You guys with me on that? But what are we really looking at here also, right? The more positive something is, the easier it is for it to reduce, the more it wants to get reduced. You guys with me on that one? That's what point number 3, I think, said on that list there, right?
Hold on though. The zinc thing is written, it's written as a reduction as well. Wouldn't it need to be the oxidation to react?
Yes, but that, look where it says, will zinc solid react, right? So will this react with that?
Yeah, but we still have to flip it around.
Yes, we do, right, that's the point, yes. Yeah, so
And if we flip it around, then their values are extremely close.
right, but you're saying if I multiply something by -1, it becomes something different. I'm saying as it is written, right? We are analyzing the tables as they are written. These are all reduction half reactions. What's up?
Again, I'm gonna ask like basically the same question just because I'm not following.
Well, let me ask you a question first then. So what question are you trying to answer in your head?
For them to react, one has to be oxidized and one has to
That's
be
correct.
reduced.
Yep.
So one of those has to be a reduction
Mhm.
and one has to be an oxidation.
That's correct, and we're trying to figure out which one it is, right?
Wouldn't it be zinc?
Wouldn't zinc be what?
The oxidized one.
No, that's correct, yeah, I'm not arguing with that.
So don't we have to flip that number around?
Yes, we do have to flip that number, but you're getting a little bit ahead of yourself, right? We're gonna do all that in just a second. I'm answering the question of will this react, right? That's what I'm asking you first.
Doesn't the fact that those numbers are gonna be really, really close when zinc is an oxidation thing, doesn't that mean that it probably?
Have I mentioned anything, it said, will these react unless they're really, really close for some reason, is that what I said?
No.
No. I'm not trying to trick you with this, right? I think you're trying to skip a step. I'm not saying you're wrong, right? You're absolutely correct. One of these has to get oxidized, one has to get reduced. But we're not saying, hey, will this react? And the first assessment we do is either by looking at the values, right, of the potentials, or doing the qualitative assessment of, hey, anything on that is up to the left will react to anything to the bottom right below. That's all we're saying here,
Okay.
right?
And
Now,
so we do that with the reductions.
correct, yes.
Okay.
Because all the tables you guys will ever see are reduction half reactions.
Okay.
And when it's talking about left and right, it's talking about the reactants and product sides.
Correct, yes.
Mhm.
Yeah. Good? Everyone with me on that one then, right? So will this react? Yes, it will, right? Because iron is above zinc, it's more positive than the zinc is there. Okay?
And if there's a half reaction with multiple components to it, does it still follow me that any of those components on the left,
Like for what, for example, what?
I don't know, for example, O2 and H2O will?
Yeah, so this is oxygen getting reduced, right? So it's always this species over here, right? Because so that's what we have to pay attention to here, right?
Okay.
Because here's water down here, right?
Mhm.
But we also see water here, right? So this is water here getting reduced.
So we're mainly just paying attention to,
Mm-hmm.
okay.
Okay. Okay. Cool. All right. So what do we need to do now? So now let's think about this, okay? So the question, as it is asked, now we can go on and do what you were talking about there, right? So will zinc react? If so, what is E naught for the reaction? So now we need to think about what gets reduced and what gets oxidized. What's going to be the cathode, what's going to be the anode, right? Now again, we can approach this a couple of different ways. The more positive the value is, right? The more positive this value, that means what? It's more likely to get reduced. And where do reductions happen?
The cathode.
At the cathode, got it? And so if that's going to be reduced, then the opposite one has to be oxidized, right? And I think you guys can see where this is going to go, right? So if this is going to be oxidized, essentially we just flip the whole thing, right? Multiply by -1. But let's pause here for just one quick second and think. There's one other thing we need to consider, okay? When this reaction happens, remember everything has to, exactly, right? Everything has to balance, okay? Now here's some good news. It's not really going to make a difference for us, because this was one of these other rules, okay? When we're talking about the number of electrons moving, it's not going to be affected by the stoichiometry, okay?
No?
No.
This seems suspicious.
No, it's not. So don't forget that if we want to balance this reaction, we're going to have to multiply that by 2 also. And so what we will get then is
So we're just multiplying the number.
we're just multiplying the actual equation itself. The potential doesn't change. This.
So that number stays the same even though multiplying the equation itself. But
Mhm.
why can't the universe just make sense for like one day?
That's just sometimes how it is, right? So if we do this, if we write everything out, 2x plus, right, plus zinc 2 plus 2b minus. Got it? Of course, do we ever see reactions with electrons as part of the equation?
No.
No, right? And they balance out on each side here, right? So we can just leave that stuff off. That'll be just fine, right? And then, oops, that's not what I wanted. Gonna work. Cool, right? So there's our nice balanced equation. Good? Now we have what's reduced, we have what's oxidized, we know what's at the cathode, and we know what's at the anode. Everybody with me still? Okay. So what happens then, right, E naught cell, right, E naught cathode, minus E naught anode, and I got 1.534 volts. Good? Again, the math is not the tricky part with these, it's just making sure you assign the cathode and the anode properly, okay? What's up?
What's the point of like changing it from oxidation to reduction if you're just gonna put it back to, like you're still gonna use the negative?
You don't have to, right? You can do, that's why I showed you guys essentially two equations here, right?
Yeah.
So what you're saying is, I just want to do this here. Okay,
Yeah.
then do it, that's
Okay.
fine. I don't care, right?
Okay.
I'm just saying this one helps me, because I base everything off of what the cathode and the anode are, right? And that, honestly, that's how most of the questions are asked also. Hey, what's going on at the cathode or what's at the anode, right? But either way, you're gonna get to the same answer.
Okay.
And I think that was just extra space for you guys. Cool. All right, so just as a little bit of practice here, there's some answers for you guys, right? But will aluminum solid react with a 1 molar tin 4 solution, right? And so all we're doing here is looking at what's on the left and what's on the right, and whether they're actually going to do a redox reaction or not, right? So the more positive something is, right, versus the more negative, what's on the left will reduce what's on the right below it. Or will react with what's on the right below it. Good? Make sure you guys feel comfortable with doing this. This is one of the key steps to solving any of these problems. Making sure you guys know what will get oxidized and what will get reduced, okay? And then there's just kind of finishing up what we just did there along the same steps. I think you guys can kind of follow through with that on here. Okay, so kind of taking a little bit of a different gear here then to kind of tie in some of the previous chapters. So we remember from, or hopefully remember, that product favored reactions, right, have a delta G less than 0, okay? And spontaneous cell reactions are going to have E naught of the cells that are greater than 0, okay? And so now we can basically start to relate delta G and E naught of the cell together, okay? And so we have our first equation here about Gibbs free energy and its relationship to E naught of the cell. N is the number of moles transferred, that's why we have to make sure that we have a nice balanced equation there, right? Make sure that you have the proper number of electrons, okay? We have a constant that comes in, right, a Faraday constant, which is equal to charge per mole of electrons. And right, this is kind of showing you guys here what the Faraday constant is, right, how we get to it down here, okay? I don't care, right, you see sometimes the book uses 96,500 and different places use 96,485. It really doesn't make that much of a difference, whichever one you guys want to use, right? But Faraday's constant is coulombs per mole, and that's going to be important to remember. Later on, we're going to ask a question about how many electrons get transferred, right, as we do a redox reaction, or how many moles of electrons, these kind of things, okay? And Faraday's constant is going to help us relate those values together. Right, so delta G naught equals negative NF E naught of the cell, okay? And F is our new constant there. I think, right? So if I give you this here, can you guys calculate delta G real quick? Well, I didn't ask you a question, so what is delta G naught?
Do we know the temperature?
We assume it's room temperature, that's fine.
Okay. No.
No? What do you mean no?
No, I do not know how to calculate.
Okay, what's the equation I just gave you? Right? Do you have E naught of the cell? Yeah. Is F a constant? Yeah. Can you tell me how many moles of electrons are transferred? Yeah. That's all, right? So, nothing too complex here, right? You just plug and chug the stuff into the equation there. Delta G naught equals negative NF E naught of the cell. We have E naught of the cell. This is a constant, right? So all we need to do is figure out N. Okay? So negative 2 moles, right? 96500 coulombs per mole, right? And then here we have 1.1 volts. Good? Any issues? Let's see here real quick. Moles cancel out with moles. And then we're left with units of coulombs times volts. Wait a minute. What values is delta G usually in? It's a measure of energy, so it's usually in
Kilojoules.
joules, right? Whoops. Do we got a problem? No. I told you guys this would come important in just a minute, and here it is, right? So, if, real quick, right, just to kind of, so if we do this, I got negative 2.12 times 10 to the minus 5 Coulomb volts, right, CVs. But if we go back for just a second, I'll scroll back. Hold on. Where was it? Here, right? So remember, 1 volt is equal to 1 joule per coulomb, right? So a coulomb volt is equal to 1 joule, same thing. Okay. We good? All right, so this is right equal to joules. All right, so I gave you guys E naught of the cell in this particular problem, right? But remember, we just figured out how to calculate E naught of the cell. So I could have asked you guys the same question, but just saying, hey, here's this battery that we made with copper and zinc. Tell me what delta G is, right? That would be the equivalent question you could ask here, okay? Now, what else does this number tell you? So we got negative 2 times 10 to the minus 5. So what else could you say about this reaction?
It's spontaneous.
Well, delta G is product, right? If we have a negative delta G, it tells us it's product favored, right? So that's something else that's important to remember here. Now, you guys already...
I thought it told us it's spontaneous.
Yeah, I mean, it tells us two things, right? In the direction that it's written, right?
Okay.
Yeah. So we also knew that because E naught of the cell is a positive value, though, correct? Okay. So remember, whenever you guys assess or whenever you guys finish with a problem, always say, hey, what does this number actually tell us, right? One of my favorite questions on the exam is always what?
Why?
Explain, right? Or why is this the case? Right? I think it's your guys' favorite question too.
Oh, for sure.
Okay, so let's think here for just a second. Let's bring in another important reaction. So we know that delta G naught is equal to negative NF E naught of the cell, okay? But if you remember, it's also equal to RT natural log of K naught, okay? So delta G, right, we learned about in the previous chapter, has a couple different definitions, so to speak, right? A couple different equations, right? So we learned that delta G is equal to negative RT natural log of K, right? But now we know that it's also equal to negative NF E naught of the cell. Do you guys see where we're going with this? So what can we do now? So what we can do now is we can relate E naught of the cell to the equilibrium constant. Okay, don't go boo. Okay, this one will be easy too, I promise. That's the good part about this chapter. It's the equations are not that complex. Okay. So I'll skip you guys the small derivation here and take you guys to the answer. Okay, 0.0257 volts per mole natural log of K naught. Okay, or 0.592 volts over N log of K naught. Okay. Okay, so two representations for how to relate E naught to the equilibrium constant. Okay? And so pay close attention. The only difference is one of these is a natural log and the other one is a log base 10. Okay? So where does the 0.0257 or the 0.059 volts come from there, right? So all that is at room temperature, right? We have R as a constant, T as a constant, and F as a constant, right? So if we're at room temperature, R, T, and F are a constant. So we just lump that all together into those values of 0.0257 or 0.059.
Where are you getting natural log as opposed to log?
Yeah, so it just depends on what specifically. Your question is, why in the world do we have two different expressions for it, is really what you're saying, right? Why would we care that one is natural log versus log? There's different reasons why we would want a natural log versus a log. So it comes from modeling purposes. So if we're actually doing data in the lab, right, sometimes we want to model based off the log versus the natural log. Right? Natural log is sometimes easier to graph, is what it comes down to make a linear plot or to do something with it, right? That's all. There's really no purpose. You can convert natural log to log. I think it's, what is it, you multiply by 2.303 or something like that is what it is. There's some constant to convert between the two anyway.
I've never been good with logs, so.
Oh, it's okay, right? So you guys with me on this? So what do we have in this equation? Well, we've got K, we've got N, and we've got E naught of the cell, all right? Now you guys know how to calculate E naught of the cell. That's what we've just been doing using our half reactions, okay? N here is the number of moles. So we have to know our oxidation states, okay, so that we know how many electrons get transferred in between the metals, okay? And what is K? K is always what? The equilibrium constant, products over reactants, right? The concentrations. And this is also going to be important, because what we're going to do in just a little bit is talk about what happens if we have different concentrations in there. Good?
Is V just unit volts?
Yeah, that's how many volts in there. Mhm. Or if you want to use a natural log, I'm doing crazy, it's just worth one time. So, do we have information about E naught of the cell? Yep. Do we know what N is? Yep. So can we solve for K? Hopefully, right? So 1.10 volts. 0.592 volts over Q log K prime, not K prime, excuse me, K naught. And so log K naught is equal to 37.16, right? Remember to get rid of your log 10 to V, right? So K is 10 to the 37.16. 1.5 times 10 to the 37 is what it comes out to be. Ooh-wee. So what does 1.5 times 10 to the 37 tell you? Massively product favored, right? Massively product favored, which makes sense. Because what did we say about E naught of the cell? If it's a positive value, right, it's going to be product favored. And the previous example, we just found out that it is, you know, delta G is negative for this, right? So all this stuff comes out to be the same answer, right? It tells us that it's product favored. Good? So, what's the purpose of these last couple of slides that we just did? Now we have multiple ways of calculating E naught of the cell. We can calculate directly from the tabulated data, as long as we know how to read what's oxidized and what's reduced. As long as we have E naught of the cell, we can calculate delta G, right? Or we can calculate K. So we can relate all three of those values, E naught, G, and K now. Yep.
So if we're using like the K and all this,
Yep.
it has to be like room temp or like constant?
Yeah, so the assumption here is that we're doing it at room temperature is what it is. When it's not room temperature, I'll show you guys next time there, right? We basically, we have to take the complete equation, not simplify it, is what it is.
Okay.
So. Good? Cool, all right. I think that's all we can at least find for today. Might as well pick up the rest of it and probably finish up the chapter on Friday there. And then we'll move on and do the organic stuff. Sound good?